Lecture 29 covers sections 9.1 through 9.6. At the end of today's lecture, you should be able to describe the behavior of an RLC circuit using second-order, ordinary, linear differential equations. For us to begin, we will work with a general second-order, ordinary differential equation. That is, the second derivative of x with respect to time plus 2 alpha times the first derivative of x with respect to time plus omega naught squared times x is going to be equal to f of t. X of t is the output of our circuit, either our current or our voltage. And f of t is our input. It can either be a constant or it can vary with respect to time. Now let's consider the following RLC circuit. We have a resistor, an inductor, and a capacitor in a parallel configuration. They're being supplied by a current source, I sub SC. I sub R is the current running through our resistor, I sub L is the current running through our inductor, and I sub C is the current running through our capacitor. If we construct a KCL equation at our top node, we'd have I sub SC would be equal to I sub R plus I sub L plus I sub C. Now to describe the behavior of these, we want to employ our constitutive equations for each component in terms of our node voltages. That is, I sub SC, our current source, is going to be equal to the current running through our resistor, which is our voltage potential established across the resistor V per our resistance R, plus the current running through our inductor, which is 1 per L times the integral from t naught to t of V of tau d tau, plus I naught, where I naught is our initial current running through our inductor, plus C, our capacitance, times the time series change of our voltage potential across our capacitor. Now to eliminate the integral, we want to differentiate our equation. If our current source is constant, that then goes to 0, and our initial current running through our inductor is also 0 when we take the derivative with respect to time. Thus, we'd have 1 per R times the time rate of change of our voltage potential across our resistor, plus our voltage potential across our inductor per our inductance, plus our capacitance times the second derivative of our voltage with respect to time is going to be equal to 0. If we divide by our capacitance and rearrange in order of our derivatives, we have the second derivative of our voltage with respect to time plus 1 per RC times the time rate of change of our voltage plus V per LC is equal to 0. Thus we have the natural response for an RLC circuit. It is our natural response because it is not forced, i.e. our right-hand side is equal to 0. The response is going to be that of then the homogeneous equation. That is, if we determine the homogeneous solution to the second derivative of our voltage with respect to time plus 1 per RC times the time rate of change of voltage plus our voltage per LC, we have then the natural response of our RLC circuit. To do such, our characteristic equation describing our second order ordinary linear differential equation is lambda squared plus 1 per RC lambda plus 1 per LC is equal to 0. Using the quadratic equation, we can solve for lambda. Lambda 1 and 2 is equal to minus 1 per 2RC plus or minus the square root of the quantity 1 per 2RC squared minus 1 per LC. Since we have two unique eigenvalues, our solution takes the form V of t is equal to a1 e to lambda 1t plus a2 e to lambda 2t, where a1 and a2 are constants. For simplicity, we will define alpha as the Neper frequency. That is, alpha will be equal to 1 per 2RC. We will also define omega naught, the resonant radian frequency, as 1 per the square root of LC. Thus, our roots become lambda 1 and 2 are equal to minus alpha plus or minus the square root of alpha squared minus omega naught squared. Thus, we are back at our original form. The second derivative of x with respect to time plus 2 alpha times the time rate of change of x plus omega naught squared x will be equal to f of t.